Okay, gentlemen, so this is the last educational video you will be viewing in this class this year, so that's good. Hopefully your brains aren't already filled. So what I'm going to do today is go over a few of the questions from worksheet number 3, the energy and changes of state worksheet. And then I'm going to go over one more advanced question that I made up and just show you how that works. So the first thing I'm going to do is just quickly go over questions 1 and 2. So one says, what is the delta H? Remember, delta H, change in enthalpy, is what it's called, but it's basically just heat. It's how much heat energy. For our purposes, delta H and Q are the same thing. What is the delta H in joules when 5 grams of water cools from 75 to 25 degrees Celsius? The specific heat of water is 4.184 joules per gram degree Celsius. Also calculate the number of calories given off by water. So there's two answers. They're pretty simple. First, you just figure out joules, then you convert to calories. But this is a temperature change problem. This is like the problems we were doing before. It's based on temperature change, not phase or state change. So it's just Q equals MC delta T. And we have all these numbers. So I'm going to set that up and come back. Okay, so I've set up the problem and the conversion. All you do is Q equals MC delta T. So 5 grams. Q equals 5 grams of water times the specific heat of water times the change in temperature, which is negative 50. It's going from 75 to 25. That's a negative change. And you get, rounding to sig figs, negative 1,050 joules as your delta H. If you convert that to calories, and I showed the conversion here, you get negative 251 calories. And I'm rounding to 3 sig figs for both of these. The way this is worded, I would understand if you thought you should put the calories in positives, because how many calories is given off by the water is kind of maybe not the best way to word that, but the answer on the bottom had you just do the straight conversion. So that's all there is to that one. This problem is just like the ones from last week, just Q equals MC delta T. Number 2 is one of the newer problems. This deals with changes of state. So how many joules does it take to melt 35 grams of ice at 0 degrees Celsius? So I probably should have done this for the first one. In fact, I will. You're supposed to draw the mini heat curve, which just looks like this, and mark where you're beginning and ending. So for this one, we're just taking water, and it's going in this area, because remember, this would be solid here. Then you have your state change, liquid here, and gas up here. So in problem number 1, it's all staying in the liquid phase. Problem number 2, if we were to draw our mini heat curve, here we're melting ice at 0 degrees. So the ice is starting at 0 degrees, and we're just melting it. We're not raising its temperature at all. So we're entirely on the first horizontal line there, the state change. And whenever you're doing a state change and not a temperature change, your equation is going to be N times, in this case, delta H fusion. If it was boiling, it would be delta H vaporization, and N is number of moles. So the delta H fusion of water is given here. So I'm going to set up this equation and come back. Okay, so I set up this equation, and I want you to take note of a couple things, because, again, this picket fence or dimensional analysis method can do a whole bunch of stuff and kind of keep everything straight. So first I found the number of moles just by dividing grams by the molar mass, but I kept this all in the same format. Kilojoules per mole, that can be a conversion factor. So if I just do convert grams to moles, I can then convert moles to kilojoules. Well, with 1 mole on the bottom and 6.01 kilojoules on top. And then if you're reading carefully, it asks how many joules up here does it take. So I have to convert kilojoules to joules, which again is just another conversion. 1 kilojoule on the bottom equals 1,000 joules on top. You don't have to set it up like this, but I find it saves space, it's less writing, and it keeps everything straight. And if you look, you could cross out grams, then cross out moles, then cross out kilojoules, and end up with joules. So it just makes everything a little more organized and work better. So you get 11,680 joules to melt 35 grams of ice, or 11.68 kilojoules if that's what it had asked you. So that's 1 and 2. Whenever you're dealing with, again, change in temperature, you're going to do Q equals MC delta T. And whenever you're dealing with change in state, it'll be number of moles times heat of fusion if it's melting, or heat of vaporization if it's boiling. Just be careful, because if you have to go back and add these things, again, heats of fusion are in kilojoules, and specific heats are in joules. So Q equals MC delta T will give you a joules answer, and generally N times delta H fusion or delta H vaporization will give you a kilojoules answer. So I'm going to do one more problem here. Number 6. How much heat does it take to warm 22 grams of ice from -10 to 0, then melt it, then raise the temperature to 100 degrees and boil it away? It says refer to problem 6 for all these 3. First of all, it should have said problem 5. I screwed that up. But I've written down all the pertinent information here. And you actually have to have all 5 of these pieces of information. The specific heat of ice, specific heat of liquid water, specific heat of steam, because they're different, because life is hard and full of disappointment, as well as the heat of fusion of water and the heat of vaporization of water. And all of this is either given to you, or you can find it on that thermodynamic data sheet that I put out for download with this worksheet. But I put all the data here. Now, what I want to point out is the easiest way to figure out what you should do with these is to draw the little heat curve. Yeah, it's kind of annoying, but, you know, draw it out. It probably won't kill you. So what we're doing, you draw out your kind of 5 line segments, and then you mark where you're going to start and where you're going to finish. We're starting in the solid portion. Remember, the first diagonal is solid, then you have the horizontal that's melting, second diagonal is liquid, and then the horizontal, that is the phase change to boiling, and then your gas, which can go up nearly infinitely as you can keep increasing the temperature of gas. So starting there, we want to raise this to 100 degrees Celsius, which means you're going to have to melt it, raise it all the way up to here, which is going to be 100 degrees Celsius. That's the boiling point. And then boil it all away. So we want to end up with gas at 100 degrees Celsius. We're not raising the temperature of the gas after that. So the problem with this, or at least the pain in the butt with this, is that we're covering 3 line segments. This one, or excuse me, 4 line segments. This one, and this one. And each of those is its own separate problem. And you have to set them up as such. So I'm going to set up each one and go through it. So I'll set it up, then I'll do the math and just come back with the answer. But starting with number 1, or, well, the section I labeled 1. 1 is raising the temperature. That's going to be Q equals MC delta T. And in this case, it'll be Q equals the mass, 22.00 grams, times the specific heat of ice, 2.060 grams per joules degree Celsius, times the amount of temperature change. Now, the amount of temperature change here is only 10 degrees. It's going up 10 degrees, and then you hit another section. So it's only the amount of temperature change within that section, not the total temperature. So times 10 degrees Celsius. For part 2, so I'll do all the math later, but part two is going to be N times delta H fusion. You're melting. So to set that up, we'll just do, again, you have to find moles first, so 22.00 grams, and this is H2O divided by 1. The molar mass of H2O is 18.02 grams over 1 mole. And then again, I like to just keep everything in the dimensional analysis, the picket fence, though you can take this and just multiply it after. But then the heat of fusion of water is 6.01 kilojoules per 1 mole. So you can actually just solve it that way, keep it all in there. It's the same thing as multiplying. It's identical mathematically, but this is how you set it up, and I think that saves space and keeps everything organized. So part 3. 3 is just going to be a temperature change. Q equals MC delta T. So Q equals 22.0 grams times. Now be careful here. Now we're liquid water, so our specific heat is 4.184. And then now we're going from 0 to 100 degrees. So the temperature changes to 100 degrees Celsius. And that'll equal some number. Again, I'm going to do all the math at the end. And finally, step 4, we're boiling away this, so it'll be N times delta H vaporization. And it'll look just like step 2, except for the last part. So it'll have 22.0 grams H2O over 1, 18.02 grams for 1 mole H2O. Move this guy over here. And then finally, and again, I'm going to keep it in this form, in this dimensional analysis, we can go from moles to kilojoules, because we have those numbers. It happens to be 40.7 kilojoules per 1 mole of, per boiling 1 mole of water. You don't have to set it up like that. You can find the moles and then just multiply separately, but I like to. It keeps everything organized. So all we have to do now is solve all these and total them up. And I'm going to do that. One thing to be careful of, some of these are going to be in joules and some of these are going to be in kilojoules, so you have to make sure to convert them to common units. Okay, so I've set up all the problems and done all the math, and you'll see the first step, that heating from 0 to 10 degrees, from negative 10 degrees, to 0, that used 453 joules. The second step, the melting of the water, used 7.34 kilojoules, and I decided to convert everything to joules, so I converted that to 7,340 joules. The third step used to raise the temperature of water from 0 to 100 degrees Celsius, used 9.20 times 10 to the third joules, or 9.2 kilojoules if you prefer. I'm leaving everything in joules. The reason I have that in scientific notation is it's the only way I can show 3 sig figs with that number. So if you don't have that exactly, it's not a huge deal, like if you rounded to different numbers of sig figs, but 3 sig figs should be the amount you round to for this. The last step, the boiling of the water, takes 49.7 kilojoules, or 49,700 joules. Notice how much more that takes than every other step. It is a lot of energy to boil a liquid, way more than just to melt that substance from a solid to a liquid. Because if you think about it, solids and liquids, both condensed states of matter, they're kind of similar. The particles are pretty close together. To get that water to all turn into vapor, you have to push those particles a lot farther apart. So that takes up more energy. And in general, changing state tends to take up more energy than raising the temperature, at least with water. So all we have to do now to find the total is literally total each of these steps. Yes, you have to do 4 equations, and it's kind of a pain, but then it's just adding. And the total ends up being, if you add all those things together, 67,700 joules, or if you left it in kilojoules, 66.7. I think on the worksheet, the answer is given in kilojoules or in joules, in the mixed up answers, but either one of these would be fine, unless the question specified, and I don't remember if it did. So that is how you do this. If it then asks you to raise the temperature of the vapor from 100 to, say, 130 degrees, you would literally just do a 5th problem. That's all you would have to do. Also, one important thing to note about any of these curves about any of the heat curves, is that this flat area represents the melting point, and this area represents, I'm sorry, I have that reversed. This area represents the boiling point, excuse me, because apparently it's been a longer day than I'd like to admit. And this represents the melting point of whatever substance you're talking about. So I could just give you a question, say, how much would it take to make water go from negative 10 degrees to 130 degrees? And you would have to understand that you're going to raise the temperature, then melt it at 0 degrees Celsius, then raise the temperature again to 100 degrees Celsius, then boil it, and then raise the temperature again to 130. And where these melting and boiling points are is different for every substance. And you have several of those on your data sheet. Now I stuck with water because it's a little easier for us to understand, but this could work with anything else. You just have a different melting temperature and boiling temperature and different heats of vaporization and heats of fusion. But you plug in the numbers all the same, and it works the same. Then you add everything together. So, gentlemen, if you have any questions about this, I will have, I'll be on Zoom or email me. This is your last homework, so hopefully you understand it. Otherwise, hopefully you enjoy your summer. I will see you later. Goodbye.